Assalamu alaikum, greetings everyone. This is Dr. Bilal Wajid. So, in the last lecture, we talked about ideal low pass, band pass, high pass filters, and a good approximation, which is the Butterworth filters. We mentioned that, well, these Butterworth filters are of an order n, where the higher the order, the complexity increases. However, the slope or the movement from the allowed zone to the zone which is present within the cutoff frequency and the zone which is outside the cutoff frequency, this transition becomes much steeper. Now, this particular lecture talks about point processing. So, chapter 3 again, it talks about space domain filtering and frequency domain filtering techniques. Within space domain, you have two general categories: point processing and mask processing. This particular lecture is about point processing. Next lecture, or the subsequent lecture, we'll talk about mask processing. And actually the lecture beyond that will talk about frequency domain processing. So, point processing in an image is, so if you have an image, the original image, and the output image, the pixel which you want to transform, only that pixel is responsible for its equivalent in the output. This is point processing. So the same point is responsible for the same point. Opposed to in mask processing, this is the same point. So now we're talking about this point in the middle. So that point and its neighboring points, all of them are responsible for the output. So that's the difference between, and this is your mask. And in this example, the mask has 9 elements, but it can have more. So it could, from a 3x3, it could be a 5x5, it could be a 7x7 mask. This is an example of a 3x3 mask. So in a point processing, the point is responsible for the point. In mask processing, the point and its neighboring points together are responsible for the point in the output image. Within point processing, you have 3 types. You have contrast enhancement, bit slicing, and histogram equalization. This is what is referred to as the equation, where the input pixel and some transformation is responsible for the output pixel. Now, in contrast enhancement, what happens is, generally in linear transformation, if this is your R and this is your S, you would have a linear line. In other words, they are pretty much the same and you didn't do anything. It's more like an all-pass filter. It's like you're allowing everything to pass, you're not changing anything. That would more look like no, that's actually not that's not exactly a good example of an all-pass filter. But however, what you're really doing is you're actually not changing anything, and it's more like a linear transformation. Well, in contrast enhancement, what you do is you preserve values which you may not be interested in. You preserve those values. So this is the point which has been preserved. But for the rest of the points, you enhance the contrast. In other words, the gray levels which are between R2 and R1, you elaborate them and enhance that difference. This is called contrast enhancement, and this could be important. For instance, if you want to do, you want to see things, you want to see a tumor more visible as opposed to its surroundings, or you want to increase the visibility of certain regions. That is contrast enhancement. One good example of contrast enhancements is what is a binary transformation, that you say, okay, regions which are present with me, gray level regions, because dark is 0, bright is maximum. So this particular region, I'm going to brighten it, or I want to increase the enhancement. This would be a binary transformation, but in this case what you're really doing is like separating a tumor region from the background. This would be a binary transformation. Now another equivalent of that would be a slight modification where you do make certain regions more visible, that's fine, but you retain the background. So you preserve the background. So the tumor in relationship to the tissues is preserved, but the tumor is also, highlighted. Here, you kind of get rid of the background, or you make it very light or dull so that only the tumor region is enhanced and is made visible. Here, the relationship of tumor with respect to other tissues is preserved, whereas you're also highlighting the tumor region. So that's called contrast enhancement. Another example is bit level slicing. So bit level slicing is, again, let's go back to this transformation of a gray region to a byte. So you have, for example, if you want to encode 256, if you want to encode two gray levels, a binary gray level, 0 and 1, you need 1 bit. Right? Because 0 would represent dark, 1 would represent 1. If you have two gray levels, in other words, you need 1 bit, but if you have 4 gray levels, you need 2 bits. If you have 256 gray levels, you need 8 bits. So 0 would represent 8 zeros and 256 would represent all ones. Now, in a gray level bit transformation, the important thing to understand here is this guy, or the leftmost guy, is the most significant bit, whereas the rightmost guy is the least significant bit. So if you slice out or you transform just the most significant bit, then it'll cause a huge change. It'll cause a huge change because this would be more in the brighter side, this would be more in the lighter side. But if you change these ones, it's not going to matter much. In other words, changing the higher bits causes a large change in the frequency domain, but it causes a massive change in color, you could say, massive change in the gray level. But changing the lower bit causes small incremental changes. So in bit level slicing, you knock off, you basically convert the images into their gray level images, or the pixel in gray level, you convert it into its equivalent binary form, and then you either remove some bits or you modify some bits so that certain areas are focused whereas others are eliminated. Obviously, going back to this example again, which bit you're modifying does change the bit level a lot. So that's bit level slicing. Again, the whole point is contrast adjustment, but in another way. The last is histogram equalization. So histogram equalization is, for instance, if you take two cell images using the same microscope, but the illumination of the light is different, then, although the image is the same, the cell images may actually be the same, but one image will appear darker than the other one because of the illumination problem, not because there's inherently something different in the cell image. So one way of resolving this problem is you do what is referred to as equalization, where you try that the histogram, the gray level histogram, is equalized. Now in chapter number 1 we discussed image histograms, that if you have if you have these 9 pixels, then the probability of this, which is the whitest region, is 1/9. The probability of the darkest region is 3/9, and the rest of them is 5/9. This is what the image histogram would look like. Now, equalization would in fact try that almost. Now, this was an easier example because you had only 3 gray levels, but the whole point is that you try to have more of a uniform distribution function, or uniform, so that the difference in the gray levels is not what confuses you in differentiating one image to another, and you can see them in the same, you could say, lighting. So what you really do is you pass it through a transformation. Now obviously darker images, you can see here, darker images in a gray level of 256, the darker images will have higher density function, higher probabilities here, whereas very light images will have higher probabilities on the right side of the histogram. So one way of equalizing it is you pass it through a transformation. This is an example of a transformation. As you can see, it's monotonically increasing. Therefore the order of the gray levels in the image are preserved, but it does in fact give you more of a balanced histogram. So as an example, if this is your original image histogram, after passing it through this transformation, this is what it would look like. So it has tried to provide more of a uniform histogram than the one that we see here, and this is in fact very useful if you're comparing 2 images that have been taken in the same apparatus using the same equipment, but you want to somehow equalize them before you start to see them and compare their differences. So that was about point processing. The next lecture we will talk about mask processing. Again, in this particular point, it's only one element corresponds to one element, but in the mask, it's the point as well as neighboring points which collectively are responsible for the output. See you in the next lecture. Thank you very much. Assalamu alaikum.